All right. Today we are going to cover the last topic. We probably won't get it completely covered, but we will by the end of the day tomorrow. Okay? The last topic in the chemistry unit is the mole. Okay? Now, the mole, okay, is a chemical unit of measurement. Okay? It tells us approximately the amount of a certain substance that we may have. Okay? Now, are there lots of ways to measure the amount of something? Could we use mass to measure the amount? That's usually the most common way. That would give us the amount in grams or kilograms. Okay? We can also measure volume, how much space it takes up. Okay? That's usually measured in liters. Okay? But the purpose of the mole is to express the amount of something in terms of the number of particles that would be involved. Okay? Now, when we're talking about atoms and molecules, are we talking about things that are really, really small? Really, really. Okay? Which means when we're talking about how many molecules or atoms of something, that is a gargantuan number. Okay? Like, for example, if I had enough water to fill the cap of a water bottle, that would be around 20 milliliters of water. Okay? That amount would have close to this many molecules of water. Okay? 6.02 times 10 to the 23. That is 602 with 21 zeros behind it. Is that a big number? Like, huge. Okay? And that's in 20 milliliters of water. 18.02 actually. Okay? It's about the cap of a water bottle. Okay? That's a lot. We're talking about things that are very small, and even very small amounts contain huge numbers. So, the idea of the mole was invented to deal with that. This is the amount of particles of anything in one mole. Okay? That number works just like a dozen. Okay? If I have a dozen eggs, how many eggs do I have? If I have a dozen donuts, how many donuts do I have? It's always 12, isn't it? Doesn't matter what it is. If it's a dozen, it's 12. Okay? If I have a mole of something, that's how much I have. Always that number. Works exactly the same. Okay? If somebody says I have 1 mole of water, they have this many molecules of water. If they say I have 1 mole of sodium, they have this many atoms of sodium. Okay? It's that number. It's always that number. A mole is always that number. Okay? That number is Avogadro's number. We'll talk about Avogadro. Okay? I don't know why he used the mole, but when you see his picture, you might have an idea why. Okay? He doesn't have a big mole. I'll show you a video of a guy with a big mole. But he looks like one. Like the animal. Like the little burrowing animal. He kind of looks like a mole. I bet it was his nickname or something. I don't know. I just feel like it. Okay? All right. So the mole is a unit for measuring number of particles. We are going to go over the mole equation today. So we're going to get a little mathy. Not real hard math. Okay, it's a little bit of algebra. Okay, but we will use the mole equation to solve mole equation problems. Good news, there's only 4 ways I can ask a mole equation problem. Okay, and over the next few classes, however that looks, okay, I will go over at least 1 example of each way every day until the unit is over. Okay, so when I do an example, you should write it all down. And you should try it yourself. Now we have lots of examples to refer back. Okay. Questions so far? Okay, so as I was saying, the mole is a unit of measurement. This is the number of particles in a mole. Whether they're atoms or molecules, that's the number, Avogadro's number. Now, you're probably looking at that number and going, wow, that is a totally random number. It's actually not. It seems like it when you look at it, oh, man, what a random number. Okay, but here's how Avogadro got that number. He wanted to have some unit of measurement, like a dozen, that worked for numbers of particles. So he used the simplest element to calculate this number. Okay? He said, I want to calculate the number of hydrogen atoms in 1 gram of hydrogen. That's going to be my magic number for everything from there. Okay? So if you look up here on your periodic table, the atomic mass for hydrogen is just barely over 1 gram. Okay? That's because if I have 6.02 times 10 to the 23 hydrogen atoms, they will have a mass of 1 gram. That is true for every element on the periodic table. If I have 6.02 times 10 to the 23 atoms of lithium, it'll have a mass of 6.94 grams. Why is it more? Well, sort of more dense. Is an atom of lithium bigger than an atom of hydrogen? Yeah, it is. No? Okay. Like in a hydrogen atom, what is there? 1 proton and 1 electron. It's the simplest atom. That's why it has the smallest mass. Okay? But if I have a lithium atom, okay, a lithium atom has 3 protons, 4 neutrons, and 3 electrons. It's bigger. There's just more stuff there. Okay? So if I have the same number of lithium atoms, it's going to be heavier. There's more stuff there. Does that make sense? You can kind of see that pattern follows, right? As you go along the periodic table, as the atomic number gets bigger, the atomic mass generally gets bigger. There's a few exceptions for things that have lots of neutrons in them, but generally they get bigger as they go along. Okay? Every one of those atomic masses, okay, we call them atomic because we're dealing with single atoms, but they're actually also what we call the molar mass, the mass of 1 mole of that substance. Okay, so for everything on the periodic table, atomic mass is, this is the mass of this stuff if you had that much of it. 6.02 times 10 to the 23. Okay, everybody all right with that idea? All right, now, when we write mole, okay, because we're very busy, we abbreviate mole as mole. We don't have time to write the E. Okay, in the same way that we use this for at. Right? Because we're too busy to write the whole word. Very easy. Okay? So the abbreviation is MOL, moles. Okay. All right. Now, you don't have to memorize Avogadro's number. You're going to use it a lot, so you probably will, but it is on your periodic table as part of your data sheet. Okay. Okay. The mass of one substance is known as that substance's molar mass, the mass of 1 mole. Okay? And that is always going to be in grams per mole, because it's the mass of 1 mole. All right? So as we said, for all the elements on the periodic table, we can look those numbers up. Okay? Their atomic mass is the mass of 1 mole of that element. What if I have a compound? How do I figure out what the mass of 1 mole of a compound would be? Compounds aren't on my periodic table. Yeah, the total mass. You put all the stuff together, element by element. Okay? So let's use water as an example. In a molecule of water, how many hydrogen atoms are there? 2. Okay. So every hydrogen atom is 1.01 grams per mole. But I have 2 of them. So 1.01 times 2. Plus, what's the atomic mass for oxygen? 16. Okay, 1.01 times 2 is 2.02 plus 16. 18.02 grams per mole. In other words, if I had 18.02 grams of water, about the amount that fits in a molecule, I would have 6.02 times 10 to the 23 molecules of water. Okay? Is that calculation super difficult? How many people are on a calculator? Okay. Tomorrow, everybody's hand should be up. Everybody bring a calculator tomorrow. We're going to be using our calculators a lot. Okay? When we're doing the mole equation stuff, so you're going to need your calculators. Okay. So let's try a different one. Let's have you guys try this one. Calculate the molar mass of magnesium iodide for me. how many magnesium atoms in this molecule? Just one, right? I mean, we know how to do that. We have to do that when we're balancing chemical equations, right? We have to read how many. Okay, there's one magnesium, so that'll be 24.31 grams per mole for the magnesium. All right, how many iodines are in there? 2. 176.9? 126.9. Oh, that's close. 126.90. And there's how many? 2. All right, so times 2. All right, so all we do then is punch that in. Okay, so we go 24.31 plus 126.90 times 2. Okay, so if I had 1 mole of magnesium iodide, it would have a mass of 278.11 grams. Okay, the units for molar mass are always grams per mole because we are talking about the mass of 1 mole. Okay? All right, try this one. Lead 2 chlorate. So as we do with any compound, it's element by element. It's the only way we can do it. We don't get the molar masses for polyatomic ions, so we just have to pick it apart piece by piece. Okay, so for lead, we're like 270, right? 207.2. All right, how many leads in here? Just one. All right, so 207.2. All right, how many chlorates? 2. Right, there's 2 chlorates. There's 1 chlorine in each chlorate. So 35.45 times 2. There's our 2 chlorines. Plus, how many oxygens? 6. Okay, so 16 times 6. All right, put all that together. So 207.2 plus 35.45 times 2 plus 16 times 6. All right, 374.1 grams per mole. Okay, is that making sense? Right? I mean, it's not super mathy.
Is there a starting?
Oh, there are some isotopes of lead that make that number, it's less accurate than the others. Like it only goes to the 10th position where most go to the hundreds. Different isotopes are constantly causing that number to change. Okay? Like for example, oxygen on your periodic table is listed at 16. On most accurate ones, it's 15.994. It all depends on your percentage of the isotopes of that element, how far you go, what that number will be. They put an asterisk beside that because it's still coming up with different numbers. Okay, for these 5, calculate the molar masses. I'll give you a little time to get ahead of me, okay, and then we'll go through them together. Okay, so for number 4, okay, I've got ammonium sulfate. Now, this gets a little crazier the more brackets and polyatomic ions and stuff like that that you get. Okay, but element by element is always what's going to work. So in this compound here, let's start with nitrogen. How many nitrogens are there? 2. Okay, there's 2 ammonium ions, so there's 2 nitrogen atoms. 14.01 times 2 plus, how many hydrogen atoms are there? 8. So 1.01 times 8 plus, how many sulfur atoms? Just 1, yep. Okay, so 32.07. And how many oxygens? 4. 16 times 4. Okay, element by element is the only way you do it. Okay, it doesn't matter how crazy the stuff gets. 14.01 times 2 plus 8.08. Okay, the 8 hydrogens. Plus 32.07 for the 1 sulfur, and then plus the 4 oxygens. Okay, so 132.17 grams per mole. Okay, questions on that one? All right, and then for our last one here, we got scandium carbonate. Okay, so how many scandiums are there? 2. 44.96. Okay, 44.96 times 2 plus, how many carbon are there? 3. Okay, so 12.01 times 3. How many oxygen are there? 9. Yeah, 3 times 3. 16 times 9. Okay, times 2 plus 12.01 times 3 plus 16 times. Okay, so 269.95 grams per mole. Okay, that's a pretty fundamental skill when we're dealing with mole equation problem solving. The molar mass of the material is something you will always be able to calculate in any mole equation problem because you can read it off the periodic table. So it's something you'll always have. Okay, when you get to Chem 20, doing these kind of calculations is part of what's called stoichiometry. Okay? Stoichiometry is calculating like what mass of all the products you would get. If you know you start a reaction with X many moles of this and X many moles of that, you know how many moles you'll get in the products, and you can actually calculate the mass of each of the products that you would get using this idea. We don't do any reaction stoichiometry in Science 10, okay? But we do just the mole equations. All right. Any questions on that? Okay. When we were doing reactions last week, okay, and we were learning how to balance them, we were putting in these big numbers, the coefficients, okay? When we put in those coefficients, it can mean more than one thing. We looked at it very, very literally last week. And we were looking at it like, okay, there's one molecule of nitrogen gas, and it's reacting with 3 molecules of hydrogen gas, and it's producing 2 molecules of nitrogen trihydride. Would I even notice that reaction if I had 1 molecule and 3 molecules? It's a pretty small amount, right? I'm not going to notice that, okay? Those numbers don't have to be that literal. This could also mean 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of nitrogen trihydride. That's a much bigger amount of everything. That reaction I'd be able to observe, okay? Because I'd be talking about 14 grams, or actually 28 grams of nitrogen. I'd be talking about 6 grams of hydrogen gas, and I would get 34 grams of nitrogen trihydride. Okay? These are bigger amounts. I'd be able to actually observe that. Either way, the reaction can be interpreted to mean that. Okay? Those coefficients are just a factor. Okay? It just means I have 3 times as many of this as I have of that. Okay? All right. So that's particles, okay, and then moles and mass and all of that. Okay, that's Avogadro. Right? He looks like a mole. Absolutely does. And like the sunken eyes and the tiny little shoulders. I don't know if it's just the cut of his suit or what there, but he looks like he could burrow underground. Okay, now, just for a little laugh. So, Avogadro, he's the guy who came up with the idea of the mole. He used hydrogen gas as the model. That's how he got that number, Avogadro's number, 6.02 times 10 to the 23 particles in a mole. All right, so now we're going to look at, okay, we're here in a second here, we're going to look at how the mole equation works. But I'm going to give you guys about 3 minutes here. Just get up, walk around, take chat, whatever, and then we'll get into the mole. So, next thing we're going to talk about is the mole equation. Okay, we just learned how to calculate one part of the mole equation, and that is molar mass. Okay, so molar mass is actually big M. Okay, the mole equation is set up like this: N equals little m divided by big M. All right, so what I need you to do is copy everything that's on this slide right here, okay? Especially these parts where we talk about what each part of that equation is. N is the number of moles, M is the mass in grams, and big M is the molar mass, grams per mole, that thing we just learned. Okay, I'll give you a minute to get that copied down. So what the mole equation lets us do is, using the mass that we might have of a known material, calculate how many moles there are. Or conversely, if I know how many moles of something I have, and I know what I have, I could calculate the mass that it would have by simply rearranging the equation. So doing a little algebra, and I really do mean a little. There's not a lot of algebra to move around a 3-variable formula. Now, I know probably some of you are looking at this formula and thinking about what the well-meaning but misguided grade 9 teacher who taught you the triangle told you. Okay? How many people know what I mean when I say the triangle? Okay, all right, inside my head, boys. All right, triangles suck. Okay? They're useless. You're going to stop using them right freaking now because they're bad, okay? Yeah, sure, for a 3-variable formula, yeah, you could do this. You could put an m on the top and an n there and a little m there. But here's the problem with that. It's not going to work when we get to this equation. And by the way, you're also going to use that one in math, okay? Or this equation. Or pretty sure you can't put roots and pluses and minuses in a triangle. These triangles are stupid, okay? And we're not going to use them anymore, okay? We're going to learn how to do algebra, because algebra ain't that hard, okay? There's 3 little rules that you need to remember to do algebra, okay? And I mean it when I say they're simple. Guys, you're looking at a guy who is not good at math. I teach physics. I don't have to be good at math, okay? I can do algebra. I use these same 3 rules. They got me through university, except for calculus. That I memorized the examples in the textbook and wrote them down on the final exam and got part marks for method. It was better than half the class, so I passed. That's what the curve's for. Okay, yeah, I'm not a super strong math person. Okay, but I can do algebra. I can manipulate equations around, and that's all you need to be able to do, as long as what you're doing is linear. That's all of high school science. Okay, it even goes into university. Okay, I got through university physics on these 3 rules, and I didn't do too bad either. Okay, I didn't have to be able to, well, even do the stuff you're doing in Math 10 right now. I can't help you with that. Okay? Math 10 for me was a long, long time ago. We were learning how to make rocks round so they would roll better. Okay? So it's not something you have to be an incredibly good math person to do. It's just 3 rules to remember. So let's say that I wanted to manipulate this equation instead of solving for n so that it solved for little m. What would I have to do to isolate little m? Multiply both sides by big M. If I want to get little m by itself, I'm dividing little m by big M. One of the rules of algebra is if you want to move something, do the opposite. Right now I'm dividing by big M. If I want to move it, I do the opposite. What's the opposite of divide? Multiply. Okay, so I would multiply both sides by big M. Now I got a big M on the top, big M on the bottom. Second rule of algebra, the golden rule of algebra. What you do to one side, you must do to the other. Okay, well, I multiplied that side by m. Gee, look at that. I just manipulated that equation to solve for little m. That wasn't so hard. And I only used 2 out of the 3 rules of algebra for it. Okay, we actually don't need the 3rd rule until we get to physics. Okay, we're going to talk about them anyway. In fact, I want you to write them down right now. Okay, these are the 3 rules of algebra. They will help you, and they're not hard. Okay, so let's look at an example that would have to use all 3 of these, okay? This is the graphing equation. We're going to use this when we get to physics. I don't know if you've gotten this far in math yet or not, but you will, okay? In Math 10, you go over this. It's the equation for a linear function on a graph, okay? Let's say, right now, this equation solves for y. I want to solve for m. Right now, what's attached to m? X. Okay, so I should move what first then? B, because the third rule says move what's not attached first. B's not attached. Okay, right now I'm adding B. First rule of algebra, if I want to move it, do the opposite, subtract. Okay, so if I subtract B from this side, B minus B is 0. So it cancels out. Okay, and then I go over to this side. Y minus B, second rule of algebra. Do it to both sides. Y minus B equals m times x. I still want to get m by itself. I'm multiplying by x. How do I move x? Divide. Okay, so when I divide this side by x, x divided by x is 1. What's m times 1? M, right, so that effectively makes that x go away. And then, what I do to one side, I do to the other. Now m's by itself. That wasn't that hard, was it? Okay, eventually, guys, you'll get to the point where you could do this. Manipulate that. That's the Doppler effect formula. They do that in physics 1. Okay? You would know whether you were plussing or minusing before you had to do anything with it. Okay? We get into formulas like that. Okay? For sure. It doesn't matter how complex the formula gets. You're moving one piece at a time using these 3 rules. Okay? It's really not as hard as you may have been led to believe when someone taught you a foolish trick. Okay? A foolish trick that only works 10% of the time if you're lucky. Okay, so we're going to use algebra. The mole equation in the end, the mole equation is not very difficult, okay, because when we're using this equation, you only ever have to do one manipulation of it. You're either solving for n, which is what it's set up for, or you're solving for mass, which is the manipulation we just did. You will never use this equation to solve for molar mass, because you always get the molar mass off the periodic table. It's never an unknown. Okay, so using this formula is really easy. You only ever have to solve for n or little m. Everybody with me there? Okay. As I said before, there are only 4 ways for me to ask a mole equation problem. Okay, I'm going to go over at least one example of each every day until the end of the year. All right, so you'll have lots of examples of each kind. Okay. Some of them, there's the first 2 types only involve using the mole equation. The second 2 types involve using Avogadro's number, the 6.02 times 10 to the 23. That's why we learned that number. There's a little bit of math that goes in with that. Okay. I would like you to write this example down. Okay. We're going to do this as our first example. This is a mole equation type 1. Mole equation type 1 example. It's the easiest. In any problem-solving question in science, the first thing we want you to do, and we'll give you a mark for it, is to write down your givens. That is, what numbers or values does the question give you outright? Okay? So this question wants to know how many moles. What part of the mole equation is moles? N, little m, or big M? N. Oddly enough, the one thing in the whole mole equation that doesn't start with M, yeah, is N. N is the number of moles. It's the dumbest equation ever. Okay, so N is the number of moles. That's what this question wants me to find, number of moles. It tells me it wants to know how many moles of calcium chloride are in 90 grams. The 90 grams is what part of the mole equation? Little m, yeah. Okay, little m is always in grams. And because they told me it's calcium chloride, can I calculate the molar mass? Okay, that's what we learned how to do a minute ago, right? So I go, all right, I got calcium chloride, so that's 40.08. There's only one of that. There are 2 chlorines. Pretty sure. 110.98. Okay, grams per mole. So I've got these 2 values. Well, I kind of had to calculate that one. You would get a mark for this. Okay? Do I have to do anything with the mole equation? Or can I just plug in my numbers? Right. I don't have to manipulate on this one, right? The mole equation is n equals little m over big M. I'm looking for this and I have those 2. So I don't have to do any algebra here. I just have to plug my numbers in. Okay? So that's going to be 90 grams divided by 110.98 grams per mole. Okay. When I divide those 2 numbers, first off, do I have more or less than 1 mole here? Less, yeah. I have 90 grams. 1 mole has a mass of 110.98 grams. So is it okay if I get a decimal? Okay, always a good idea to kind of check that over in your head logically so that when you punch it into your calculator, you can go, okay, that number makes sense. I probably did it right. I mean, you're never going to be sure 100% on the number, but at least if you know this should be big or this should be small, you know if you're on the right track. Okay, so I should get a number less than 1 here. I have less than 1 mole. What are my units going to be? I'm dividing grams by grams per mole. Moles, right, the grams are going to cancel, okay, and I'm going to be left with moles, which is what I'm looking for, number of moles. Okay, so if I punch those numbers into my calculator, okay, I'll have 90 divided by 110.98. Okay, that fits with what I thought. It is less than 1. I have less than a mole here. I have 0.81. 2 decimal places is good enough. 0.81 moles. Okay, that's a type 1 problem. Pretty easy. Don't have to do any algebra, you're just plugging in numbers. Okay. Questions on that? Anybody need that up anymore? Okay. Write this one down. This is a type 2 problem. Okay, so in this one here, they want to know the mass. Which part of the mole equation is mass? N, little m, or big M? Little m, right. Okay, so in this one, we're looking for little m. They tell me I have 4.5 moles, so they gave me N, right. And they told me the material. It's magnesium bromide, but they wrote it in words. What have I got to do? I got to write it properly. I got to drop and swap this ionic compound. So being able to do that is still pretty important. Okay, MgBr2. This is a +2. That's a -1, right? All right, so got that. Now I can calculate the molar mass of this stuff. So that will be, I've got 1 magnesium, so 24.31 grams per mole, plus 2 bromines, 79.9 times 2. $184.11. Okay, so I have N, and I have big M, and I'm looking for little m. So, little m over big M. So you would get a mark for this, and now you're going to get a mark for your algebra, because you have to do a little bit of it. Okay? I've got to take big M, and I've got to move it. What am I doing? Multiplying or dividing? Right, I'm going to multiply both sides by big M. So now it's over here. So you would get a mark for this Or if you just plugged in the numbers and went 184.11 grams per mole times 4.5 moles. Okay, now I've got moles on the top, moles on the bottom. When I multiply those, the moles are going to cancel, and I'm going to be left with grams, because that's what mass is measured in, right? I should get grams for my number. So take my 184.11 and I multiply it by n, 4.5. Okay, so I have 828, we'll round to 2 decimal places, 0.50 grams. Okay, so this question would probably be like a 3-mark question. You would get a mark for your algebra / math, mark for your answer. Any questions on how that one worked? Okay. Types 3 and 4 still ask you to do these two things. N equals little m over big M, or this manipulation. But they add in an extra step. The extra step involves using Avogadro's number. Okay, so let's say that I tell you I have 2.5 moles of calcium bromide. How many molecules of calcium bromide do I have? Avogadro's number tells me how many molecules are in 1 mole, right? 6.02 times 10 to the 23. That's how many particles, doesn't matter what, are in 1 mole. I have 2.5 moles. What do I do with those two numbers? Times them, right? Let me simplify it for you. If I told you I have 3 dozen donuts, how many donuts do I have?
36.
How did you do that? You multiplied how many dozen by how many are in a dozen. Guess what we're doing here? Same thing. I have 2.5 moles. I multiply by how many are in a mole. It's just a different number. It's the same operation. Okay? People get all thrown by it, but it is not at all any different than what I just asked you. I have 3 dozen donuts. How many donuts? 3 times 12 is 36. Oh, there we go. Okay? Well, if I want to calculate how many molecules of this there are, it's just 2.5 times this number. Now, you got to learn how to do that in your calculator, okay? Which we have time. Okay, if you have one of the ones that I lent you, you probably can't. Yeah, if you got a graphing calculator, you're good. You need a scientific calculator at the bare minimum to be able to do this. Okay, so make sure you have a scientific calculator for tomorrow. All right. If I want to put this into my calculator, to put Avogadro's number in, I use bracket, and then I go 6.02. Right? Then I want to get that times 10 to the power of thing. Okay? There's a quick way to do that. Hitting the second function button and then the comma. Okay? Above the comma you see 2 capital E's. When you hit that, oddly enough, you only get 1. But that means times 10, and the next number you enter is the exponent. Okay? So I would go 6.02 E23. Now, if you have a different kind of scientific calculator, you may have an EE button, or you may have an EXP button. Okay? That does the same thing if you have an EXP button. All right? So those are the buttons you need to look for. If you can't find one on your calculator, let me know. Yeah, if you have the TI-83, it's second, double E's, okay, 23. And then I just multiply by 2.5. Okay, close the brackets. All right. There would be 1.505 times 10 to the 24 molecules of calcium bromide in 2.5 moles. Okay? I could have put any compound next to that question. The answer would have been the same. Agreed? Because it doesn't matter what I have. A mole is a mole. 6.02 times 10 to the 23. It doesn't matter what I have. In the same way that it doesn't matter whether it's eggs, donuts, flowers, a dozen is always 12. Okay, good work today, guys. We will go over type 3 and 4 tomorrow, and then I'll do another example of each type, and then we'll kind of get to work on it a bit.